This is your Algebra 1 Exploring Functions Study Guide review. Number 1, which relation is a function? Here we have a mapping diagram. We have 4 of them. In a mapping diagram, to determine if it's a function, we want to look at the first column, this first bubble. This is your x bubble. These are where your inputs are located. And we want to see, do we have more than one arrow coming off of an x? Do we have more than one arrow coming off of an input? Because that would mean that it is being paired with 2 or more y values. And in a function, that can't be the case. Remember that our definition of a function is that each input is paired with exactly one output, or each x is paired with exactly one y. So if we look at A, we see that 3 is being paired to both 3 and to 7. So this does not meet our definition of a function because it is going to 2 outputs instead of only 1. When we look at B, we can see that 4 is only going to 1, that negative 1 is only going to one number, the negative 5 is only going to one number, and 3 is only going to one number. So by our definition of a function, this would fit. Each input is going with exactly one output. For C, we can see that 5 is going to 2 outputs, meaning that that is not a function. And we can see that negative 5 again on D is also going to 2 outputs, meaning that that is not a function. When we look at 2, this is a table. It says, which of the following tables is a relation that represents a function? Well, in this table, we are looking to see if the x values repeat. So in A, we see that 1 occurs twice. It is going with 0 and with 2. So by our definition of a function, this would not cut it. Looking at B, the same thing is true. We see that 10 is going to 2 y values. It's going to 3, and it's going to 1. So that is not a function. When we get to C, we can see that 6, 5, 4, and 1 are all appearing only once, and none of them are repeating. So this would be a function. It does not matter that the 6 repeats in the y column. Our focus is going to be only on the x when we are determining a function. And so looking at that, we can see that again. In D, 7 repeats, making that a non-function. When we look at ordered pairs, such as 3, we're trying to determine if they are a function. What we need to look at is, again, the x values. Do any of those x values repeat, and are they going with a different y value? So in this first one, we can see that 2 is appearing twice, once with 1 and once with 8, so that would not be a function. In B, we can see that 5 is appearing twice, once with 3 and once with 7, so that would not be a function. Again, we get to C, and we see that negative 5 is repeating, and we also see that negative 2 is repeating. So that would not be a function. When we look at D, we can see that each of these is only occurring once in this table. So by our definition, that would be a function. So D would be our answer in this particular case. When we look at 4, we want to know which relation is a function. Looking at graphs, in order to determine if a graph is a function, it has to pass something called a vertical line test. What the vertical line test is that if you take a vertical line and you place it anywhere on your graph, it should only intersect at one spot. So looking at our graph, we can see that at any point on A, it is only intersecting one time. It will never intersect more than once. So by our definition of a function, A would be a function. So A would work because it passes the vertical line test. Looking at B, B almost looks identical to A, so you kind of have to watch out just a little bit. But our graph in this case is both the absolute value function that is graphed here and this point. Both of those make up our graph. So if I were to put the vertical line test, at every point except for this spot right here, it would intersect once. But here, we can see that it intersects both on this part of my graph and on the point part of my graph. So for this particular one, it intersects at 2 spots on my graph, making this not a function. So even just that small extra little added detail of a point could make something become a non-function. Looking at C, it's obvious to see that it is crossing twice, making it not a function. Now, it's important to look at D, and to not forget that there are parts of this that are made of vertical lines. And so when you go to put your vertical line on these particular sections, it's going to intersect at every single point that is along that line. And remember that there is an infinite amount of points in a line. So in this little section right here, there is an infinite amount of points that are being intersected by your vertical line, which is why this is not a function. Looking at 5, it says, which of the following relations describes a function? Well, when you're looking at a word problem, it's important to kind of make the situation relevant, to maybe come up with some data. So identify your independent variable, identify your dependent variable. And in this case, it really doesn't matter when we're talking about baby's gender and year born, because neither one of them affect the other. So if I'm looking at a baby's gender, so a baby can be born male or female, boy or girl, and there are several different years. You can have a baby born in the year 2018, which was this year, maybe 2017, 2016, 2015. Okay, when we're looking at this, you could have a baby, a male child born in 2018, but you could also have a male child born in 2017, you could have one born in 2016, you could have one born in 2015. So by our definition, our output or our input here, our dependent variable is going to more than one outcome, more than one output. So this would not be a function. So A would not be considered a function. When we look at B, we'll do the same thing. We're going to come up with our data. So for B, it says the number of students in a gym and the different times of day. Okay, well, the different times of day would probably be our independent variable, because we like to make time independent. So at different times of the day, this could be at 12 p.m., this could be at 1 p.m., this could be at 10 in the morning. Okay, and then you could have a variety of different people in the gym. So I could have 30 people in the gym. I could have 20, I could have 40, I could have 10, I could even have 2. Okay, well, let's look. At 12 p.m., I could have 30, but I could also have 20. That's reasonable. I could also have 40. I could also have 10. We could also have 2. So in this particular case, this would not be a function, again, because our independent variable, our input, is going to more than one output, more than one dependent variable. So B would also not be a function. Okay? When we look at C, it says the number of bikes in the bike rack and the number of tires. Okay, well, a bike rack is where you place your bikes. You could have 0 bikes in the bike rack. You could have 1, you could have 2, you could have 3, you could have 4. Okay, this is a little bit different though. If you have 0 bikes in the bike rack, you're not going to have any tires. If you have 1 bike in the bike rack, you are going to have 2 tires. If you have 2, you're going to have 4. If you have 3, you're going to have 6. And if you have 4, you're going to have 8. You will not have 1 bike and 4 tires. You will not have 2 bikes and only 2 tires. So in this particular case, this would be a function because each of your inputs, which is the number of bikes, is paired with exactly 1 output, the number of tires. So C would be a function. When you look at D, where it says the diameter of apple pie and the number of apple slices, okay, well, I can have a diameter of 2 inches, I can have a diameter of 3, a diameter of 4, diameter of 5. What this does not do is that this does not affect, the diameter of my pie does not affect the number of slices that I can cut it into. So I could cut a 2-inch diameter pie into 2 slices. I could cut it up into 3 slices, 4 slices, and so on. And so I can see that again, my input is going to more than one output. It has multiple outcomes. And in a function, that just can't be the case. So D would not be a function. It says, and number 6, it says, which of the following relations does not represent a function? What I would start off with on a problem like number 6 is to take care of your obvious ones. It is easy for us to tell if a table, from ordered pairs, from a mapping diagram, and from a graph, if it is a function. And then go to the word problems a little bit later on. So, looking at B, we want to determine if this is not, remember we're looking for if it does not represent a function. So, in order for it not to be a function, the x values would have to repeat in the table. And we see that none of them are repeating. We see that 4, 3, 2, and 1 are only occurring one time. So B is a function. So this is not a choice that we're going to pick. Again, we're looking for which one does not represent a function. You have to focus on that word not on this case. Okay, if we jump to C, again, we're looking to see do any of the x's repeat. And we see that in this case, the 2's repeat, and they're going with multiple outputs. So this would not be a function. So that would actually be our answer for this one. But let's go ahead and check the other 2. When we're looking at a graph, remember that we're looking to see if the points, if they pass, okay, the vertical line test. Now, we have discrete data here. Remember that discrete data is when you have data points that are not connected. Again, you're still going to check to see if it passes that vertical line test. So you draw your vertical line anywhere on your graph, and at any point it should only be intersecting one point, and in this case it does. So this would also be a function. Now, when we look at A, it says the plumber charges $50 for a service call and $25 for an hour. So if we were to put these values into a table, okay, we could see that this would actually be a function. So if there were 0 hours, the person is still having to pay for the service call. If there was 1 hour, you're paying for the service call plus the $25 fee, which is $75. And you would see that if you continued that, you would see that each input, each of your domain, the number of hours, is only going with one outcome. So that would also be a function. Looking at 7, it says all of the representations model a relation. Which relations represent a function? So again, go to your table. Do any of the x values repeat? And in this particular table, they do. We see that 2 is occurring twice. It is going with 3 and it is going with 6. So this table would not be a function. So go down to your answer choices and you can cross out A and you can cross out C, because both of those are saying that that particular table is a function, and we know that not to be the case. So then we're going to check to see, is it only 2 and 3 that are functions, or is it only 2, 3, and 4? Well, we know that 2 is a function because if you look at the inputs, this first column right here, we can see that each of those is only being mapped to 1. So that is a function. We know that 3 is a function because we know that if we were to draw a vertical line anywhere on there, it is only intersecting at one spot. So the question is 4 a function or is it not a function? Remember that when we're looking at ordered pairs, we want to determine, do the x values repeat? So in this particular case, -3, 2, -1, and 4 do not repeat. So that would make D our answer choice. So 4 would also be a function. So 2, 3, and 4 are functions. When we look at 8, we want to know, we see the relation is graphed on the right, Which statement best describes whether or not the relation is a function? Well, we're looking for, we're really looking at the answer choices. So we know that this relation is a function, okay, because it passes the vertical line test. So we're looking for it to pass the vertical line test. Okay, so we can get rid of answer choices C and D because we know that it's a function. And then we just have to think about this. Is the relation a function because each x is paired with exactly one y value? Or is it a function because each y is paired with exactly one x? Well, those statements mean very different things. When we say that each x is paired with exactly one y, we're starting with the x's and we're looking at the y's. So when I look at my x's of 1, 2, and 3, I can say that they are only going to one y value. And that would be true. 1 is only going to 4, 2 is only going to 4, and 3 is only going to 5. You don't have any of the x values going to more than one y value. So 1 is only going to 1, 2 is only going to 1, and 3 is only going to 1. So this would be what this one is saying right here. This would be the definition of A, where each x is paired with exactly one y. The same is not true for B. Okay, so when we say each y is only paired with exactly one x value, what we're saying is that instead of focusing on the x's, we're focused on the y's. So I could have 4, 5, and 6. Okay, well, I know that 4 is only going to 1, 5 is only going to 2, and 6 is only going to 2. So in this case, each y value is paired with exactly one x value. We know this to not be a function, again, because our definition of a function is that each x is only going to one y. So when we look at this part, we need to understand that B not B, but we need to understand that A is our answer choice because each x value is paired with exactly one y value. Okay, looking at 9, it says the order pairs 1, 81, 2, 100, 3, 121, 4, 144, and 5, 169 represent a function. What is a rule that represents the function? When you're looking at equations like this right here, your goal is going to be to plug and shove, to substitute in the values into the equation and see if they give you true statements. So what I would look at is I might set up a table. Put your x's in one, and put your y's in another. And then substitute them in. So I know that in this first one, where we have y equals x to the 8th power, I could, instead of doing y equals x to the 8th, I could do y equals 1 to the 8th. And see if 1 to the 8th is actually 81. And in this case, we know that 1 to the 8th is not 81, but it is in fact 1. So this does not represent this. This is not the equation for this function. We look at B, we do the same thing. So instead of y equals 8 to the x, we'll do y equals 8 to the first power, because x is 1. 8 to the first power is 8. So we know that that is also not going to be the case for this one. Looking at C, so on C we see that x plus 8 squared. So what we would do is we would take our x value, we would plug it in for x. So in this first one we have 1. 1 plus 8 squared. Okay, well 1 plus 8 is 9. We follow the order of operations to inside parentheses first. And then square it gives you 8 and 1. So the first one, it works. So then we want to do the same thing here. So if I plug in a 2, 2 plus 8 is 10. 10 squared is 100. So that works. If we plug in a 3, 3 plus 8 is 11. 11 squared is 121. So as we've checked a couple in the pattern, we can see that this is probably our answer choice. But let's go ahead and check D. So y equals x, 8x. If x is 1, 8 times 1 is 8. equals not 81. It equals 8. So that would not be the equation for this particular function, and C would be our choice. When we look at D, or look at 10, it says which relation is not a function. The best bet is going to be to graph it using your graphing calculator. Graph the equations and see what graphs they give. You know that a graph is a function based off of the vertical line test. When you're graphing things into the calculator, it's going to graph them as a function. So if you try to graph something and it does not graph, then we know that it is not a function because our calculator does not graph non-functions without you having to do a couple of extra steps. So when you go to graph them in, look at your graphs, graph them. If they graph, you'll know that they're a function. If they do not graph, you know that it is not a function. 11. Sally's cell phone charges a $20 line charge, and the phone costs $99. The total cost of the phone bill is a function of the number of months. What is the independent quantity variable in this situation? So you've got two different variables. You've got your number of months, and you've got the total cost. Remember that time is typically the independent variable. So time is typically the independent variable. And that is true in this case. The cell phone bill is dependent on the number of months. It is not the other way around. So in this particular case, the number of months is your independent quantity, is your independent variable. Looking at 12. Mark has already sold $30 worth of tickets to the school carnival. He has 5 more tickets he could sell at $3.75 per ticket. The function 375x plus 30 represents how much money Mark can collect from selling X tickets. What is a reasonable range for the situation? Well, we know that he has already sold $30 worth of tickets. So even if he doesn't sell any, he's going to still have $30. If he sells 1 ticket, he'll earn an extra $3.75, which would give him the $33.75. Remember that our range is not the number of tickets. The number of tickets is our domain, that is X. So our number of tickets would be 0, 1, 2, 3, 4, and 5. That would not be our range, so we can get rid of that. We also need to look at reasonable domain of range. Is Mark going to be able to sell a negative quantity of tickets? He is not going to be able to sell a negative quantity of tickets, so we know that that is also not considered a part of our range. So then it comes down to B and C. And we know that he is going to sell, that he already has $30. So even if he doesn't sell anything, he will have 30. So B is our answer choice because he will have money. And C shows him not having any money. Looking at 13, where it says, which graph has the following domain and range? Okay, for the domain, we're looking for the domain to be greater than -3. So remember, domain is from left to right. So what we like to do is we like to draw our boundaries from left to right around our graph. So we see here that our graph starts at -3, and it is not including -3 because we see right here that there is an open circle. So this one is greater than -3. So we do know that part is true. Okay? And it keeps going on forever in that direction. So we know that it is greater than our -3, and it does not stop because we have an arrow. So this one has the correct domain. Okay? When we're looking at the range, we want a range to go from -2 to 4. So remember, our range is from bottom to top. So again, we draw our boundaries from the bottom to the top, and we want our range to be confined from -2 to 4. Not including -2, but including 4. our graph does start at -2, and again, it doesn't include it because we see that there's an open circle there. It goes up to 4, and it is including 4 because our line is actually touching 4. So this one has both the correct domain and the correct range. So this is the graph that has a domain of x is greater than -3 and a range of -2 to 4. But let's look at the other graphs just to see why they are not possibilities. You have to look carefully at these graphs because they're really close, and so they can kind of be tricky. So looking at B, I know that B does not represent this correct domain and range because your domain goes from -3. It is greater than -3, but it stops at 4. You will not have any x values going past that. So this one does not have the correct domain because the domain from this one is between -3 and 4. And our domain should be all real numbers greater than -3. When we look at C, we come into the same dilemma, but this time it's not with the domain, it's with the range. We see that we do have the correct domain. It does go from -3, and it keeps going on forever, and we know that because of the arrow. But what this does is that it messes with our range. So again, our range should be greater than -2 and less than 4. Less than or equal to 4. Well, this is actually greater than or equal to -2 here. So that's one thing that kind of throws us off and messes us up. But we also have this other thing. We have this arrow that's pointing down, which means that if I were to extend it, eventually my range would drop below -2. So this one doesn't have the correct range. So this graph would not represent the domain and range stated above. Looking at D, we kind of have the same issue. So, looking here, the domain is correct. Again, we're greater than 3, and we're going on forever, so it's everything that's greater than -3. But when we look at the range, again, we want it to be greater than -2 and less than or equal to 4. Well, it is less than or equal to 4. But instead of being greater than -2, it's actually greater than or equal to -2. So the inequality on that one is off. So you really have to look at these graphs closely because it can be something as simple as it being greater than or equal to when it should have been a greater than that makes it the incorrect answer. When we look at 14, it says there is a sailboat race on Lake Geneva for a distance of 5 miles. The function h equals 3m represents the relationship between the miles and the hours traveled. What is a reasonable range for this situation? Well, our range is going to be the number of hours. We want a reasonable range. Okay, well, we know that range in this particular graph is continuous. And when we're listing domain and range for continuous data, we use an inequality. So A and B would be out because we can have all of the values that are there. So when we list an A and B, when we list it as just separate points, such as 0, 1, 2, 3, 4, 5, and 6, we're excluding all of the decimal or the fractional pieces that we have. We can have fractional pieces of an hour, and we can have fractional pieces of miles. So in this particular case, A and B would not be the best way of representing our domain and range. So we want to use an inequality so that we can get every value, all of the fractions and decimals that could be a part of our range. So looking at our range, we know that if we go 0 miles, you're going to travel 0 hours. And if you go 5 miles, plugging it into our function, you will go 15 hours. So our correct range would be from 0 to 15. The function for 15 is actually on the previous slide. So I'm going to kind of go back and forth. Okay, a function is graphed on the right. Which of the following values is not in the range of this function? So, if we're looking at the range, we want to know which ones are not in the range of this function. So, remember our values of -5, 5, 6, and 7. We want to look at the range for this one. So here's our graph down at the bottom. Okay, yours should be in the correct spot. We're looking to see if -5 is a member of the range. So, -5 is down here. And since our graph goes beyond -5, -5 would be a member of our range. So A would not be our answer choice, because again, we're looking for which one is not in the range of this function. When we look at B, again, we're looking to see if 5 is a member of our function. And 5 is. We see that 5 is on our graph. So 5 would also not be an answer choice, because again, we're looking for the one that is not a member of that function. Okay, 6 is also part of our graph. Again, it falls on the line. But when we get to 7, there is a point on 7, but remember that point is an open circle. And when there's an open circle, we are not including that point. So 6 is not a member of our range, or 7 is not a member. So your answer for this one would be D. 7 is not a member of our range. Looking at 16, we want to know which best describes the range of this graph. So if we look at A, it says all real numbers less than or equal to 10. But we see that our scale is going up by 2. So this is 2, 4, 6, 8, and 10. We know that we do have values that are less than 10, but the question is it all real numbers less than or equal to 10? Remember that that would be y is less than or equal to 10. And we know that there are values that are less than or equal to 10, but it stops at about -5. So really our range in this case is all real numbers, or all numbers that are less than or equal to 10, but greater than or equal to 5. That is what we're looking for. So A is not the choice that we're looking for. We know that it's not greater than or equal to -10 because we've already established that our graph stops or starts at -5. So we know that B is out. So we can look. We can see is it all real numbers that are greater than -5 and less than or equal to 10? Or is it all real numbers greater than or equal to 5 and less than or equal to 10? But we know that it's got to be greater than or equal to 5 because we actually have a point at -5. So -5 would be included in our range. So D would be the correct answer choice. Again, just a simple change in wording has a huge effect on your answer. We get to 17. It says a theater company can hold up to 8 people in the VIP box of the theater. For a play, the amount of money they can make C from VIP box is a function of the amount of tickets T sold. If tickets are $15 each, find the range of each of the function. Well, this would be considered discrete data because you cannot sell half of a ticket. So in discrete data, we do not write it as an inequality because the inequality includes all of the values, including fractions and decimals. And in this particular case, we can't have fractional parts of the ticket. We have to determine what our range is. Well, our range is the number or is the amount of money from T tickets that are sold. So our range is the amount of money. And our domain is the amount of tickets. So, you could sell 0 tickets, you could sell 1, 2, 3, 4, 5, 6, 7, 8 tickets, but that would not be considered your range, that would be considered your domain. So if we sold 1 ticket is $15, so $15 should appear in our range. If we sold 2 tickets, that would give us 30. 3 tickets, that would give us 45, and so on and so forth. So the biggest thing here is being able to distinguish between your domain and your range. Domain being the number of tickets, and the range being the amount of money that was earned. Looking at 8, it says an airplane has cleared for takeoff at Hobby Airport and begins to ascend in the air. The plane's height over t over time t can be expressed as the function h of t equals 2000 t. If it takes the plane 16 minutes to reach its cruising altitude, what is a reasonable range for this situation? Again, we're looking for the range. T would be the time, and the range would be the plane's height. So T would be time, and which would be your domain, and the height would be h of t, which is your range. This would be considered continuous data, again, because you can have fractional amounts of time, and you can have fractional amounts of integers. Now, we're looking for the range. Okay, and for here we have the set of all integers from 0 to 16. Okay, well that would be our domain, because the domain again is time. And we see 0 minutes to 16 minutes in our domain. We have the set of all integers from 0 to 32, but again, integers by definition are just are your whole numbers, such as 0, 1, 2, and 3, and their opposites. So -1, -2, -3, and so on and so forth. Integers do not include fractions and decimals. So it would not be the set of integers from 0 to 32. Okay, again, we look here and we see from 0 to 16. Well, again, 0 to 16, that goes with our time, from 0 minutes to 16 minutes. And time is not our range, time is our domain. So C would not be the correct answer. So we are left with one choice, written as an inequality, 0 to 32. We're including 0, we're including 32,000, and we're including all of the values in between. Fractions, integers, decimals included. So D would be the correct choice in this particular case. Looking at 19, it says, which graph represents a function with a range of all real numbers greater than or equal to -7? So we're looking at the range. We want to start at the bottom. So we want to see which one starts at -7. Well, they might all start at -7. They might not all start at -7, but let's see. It appears that all of these graphs are starting at -7. So we want all real numbers greater than or equal to -7. Well, here we have it as touching -7, so it is equal to -7. And we have all of the values that are greater than or equal to. And we know that we have all of the values that are greater than or equal to because we have an arrow that is pointing up. So that means that that arrow is going to keep going up, and any y value that's there, any range value that's beyond, will be included all the way up to infinity. We look at B, we see that the same is not true. We have all real numbers, yes, that are greater than or equal to 7, but they are less than or equal to 0. So this is not all real numbers greater than or equal to -7. This would be all real numbers greater than or equal to -7, but less than 0. The same thing would be true for C. This does not include all real numbers greater than or equal to 7, because this caps out at 2. So this would be all real numbers greater than or equal to 7, but less than or equal to 2. Now, T does include all real numbers that are greater than -7, but it does not include 7 because at that particular part of the graph there is an open circle, meaning that we're not included. So the only one that has all real numbers that are greater than or equal to -7 would be A. Looking at 20, it says which of the following is not a correct description of the graph of the function shown. We want to look at the key features. So this graph has an x-intercept at 15/4 and 0. Well, 15/4 would be just before the value of 4, because we know that 16 divided by 4 is 4. So it does appear that it has an x-intercept at about 15 over 4 and 0. This has a y-intercept of 0, 3. And we look and we see that this does have a y-intercept of 0, 3. So this is a correct description. The graph contains the graph of the function contains the points 0, 3, which we know that to be true, and 5, negative 1. Well, if we look, we can see 1, 2, 3, 4, 5, negative 1. So it does include both of those points. So that is a correct description. We look at C, it says the graph of the function has an x-intercept of 3, 0. Well, we can look at that and we can automatically eliminate that choice because we know that our x-intercept is not at 3, 0, but it is at 15 over 4, 0. So this right here would not correctly describe the graph that we have there. Okay. Okay, this is your short answer portion of your review. So, looking at number 1, it says, find g of negative 2 when given g of x equals x squared plus 3x minus 1. Remember that when the value is on the inside of the function notation, it wants you to evaluate that function for x. So g of negative 2 wants you to evaluate g of x for x equaling negative 2. So instead of x squared, you're going to have negative 2 squared plus 3 times negative 2 minus 1. Then follow order of operations to solve it. So negative 2 squared is 4 plus negative 6 minus 1. Well, 4 plus negative 6, or 4 minus 6, would be negative 2 minus 1, which would give you negative 3. So g of negative 2 is equal to negative 3. When we look at the second one where it says find f of 3 plus 2g of negative 1, what you do on this one is, again, both of those values are on the inside. Evaluate f of 3 and g of negative 1 first, then add the 2 that's on the outside. Worry about this 2, this plus 2 part, in a minute. So f of 3 would be evaluating f of x for f being 3. So f of 3 would be the same thing as negative 3 times 3 minus 4. Negative 3 times 3 is negative 9. Minus 4 gives you negative 13. So f of 3 would be negative 13. Plus 2 times whatever g of negative 1 is. So come over here, do g of negative 1. Okay, well, g of negative 1 would be evaluating g of x for negative 1. So instead of x squared plus 2x, you're going to have negative 1 squared plus 2x. Negative 1 squared is 1, plus 2 times 1, which is 2. 1 plus 2 gives you 3. So what you have is negative 13 plus 2 times 3. And then you would simplify that. So 2 times 3 is 6. 6 plus negative 13 gives you negative 7. So this particular function would be, when you evaluate it, would give you negative 7. The important thing to remember there is to evaluate the f of 3 part and the g of negative 1 part first, then put them back in for those values. So substitute in the values that you got in for f of 3 and for g of negative 1. For 3, for finding x when f of x is 11. So this is the part where it's a little bit different. So we are given f of x is 11, so what we're actually given is y equals 11. So instead of plugging it in for x, we're going to actually replace f of x with 11. So for 3, come down here, and what we'll have is instead of f of x plus 2x plus 1, we'll have 11 equals 2x plus 1. And then what you'll do is you'll solve that equation. So move the, let me get rid of this extra line right here. What you'll do is you'll evaluate it, or you'll solve it. So or inverse operation, so minus 1 on both sides to get rid of the plus 1. That'll leave you with 10 equals 2x. And then you'll divide both sides by 2. And get x equals 5. So x is 5 when f of x is 11. Same thing for 4. Find x when f of x is 42. So just like we did for 3, what we're going to do is, again, we're going to replace f of x with 42. So instead of f of x equals 2x plus 7, what we'll have is 42 equals 2x plus 7. And then you'll solve it. So subtract 7 from both sides. You'll get 2x is equal to 35. And then divide both sides by 2. And in this case, you would get 17 and a half. And that would be your answer. So x is 17 and a half when y, or f of x, is 42. Use the graph on the right to find x when f of x is equal to 4. So again, when y is 4, go to your graph and find where y is 4. What x value does that go with? Well, we see the x value that it goes with in this particular case is 1. So looking at the graph, whether you're looking for y or whether you're looking for x, look at the one that they give you. So if they give you f of x, go along the y-axis, figure out where y is at that value, and figure out where you have a point along the x-axis. And in this particular case, we have a point at 1. So x would equal 1 for this particular problem. Okay. Looking at 6, 7, 8. Again, with 6, you have 4 times f of negative 3 minus g of 0. So 4 times f of negative 3. But when you're looking for this one, what you're going to look at is, again, find where f of negative 3 occurs. So you're finding when x is negative 3. So go to your graph, figure out where x is negative 3, and figure out the y value. So in this case, it looks like that y value is at 6. So f of negative 3 would be 6. And so instead of 4 times f of negative 3, you would have 4 times 6. Minus g of 0. Well, now go to your g of x graph. Find where x is 0. So find where x is 0. That would be here. And figure out where your y value is at. And your y value happens to be at negative 2. So minus g of 0 would really be minus negative 2. And then solve that. So 4 times 6 is 24. We follow order of operations. Minusing a negative is the same thing as adding. So 24 plus 2, which would give us 26. Same thing for f of 5 and for g of 5. So when we're given f of 5, we go and look where x is 5. So in this case, when x is 5, y is 2. So f of 5 would be 2. Go to g of 5. So when x is 5, y is 4. So g of 5 is 4. And 2 plus 4 gives you 6. So find out what each of those functions is first. Then use those values to solve the expression that they're given. In 8, it says you have 8 cups of flour. It takes 1 cup of flour to make 24 cookies. The function c of f equals 24f represents the number of cookies c that can be made with f cups of flour. What are the domain and the range written as an inequality? So when you're looking at the domain, that is the number of that's the number of cookies that you can make. And we have to determine, is this a continuous data or is this discrete data? And in this particular case, it's discrete data because you're not going to make half of a cookie. So I know it says write it as an inequality, but we're not going to write it as an inequality because that would not be the correct way to represent this. what we're going to look at is what would be a reasonable domain. So we have 8 cups of flour. So my reasonable domain is that I could use 0 cups of flour and make 0 cookies. Okay, I could use 1 cup of flour and make 24 cookies. I could use 2 cups of flour and make 48 cookies. There we go. I could use 3 cups of flour and make 72 cookies. And I could continue that all the way up to 8 cups of flour and 272 cookies. So your domain, reasonable domain, would be 0, 1, 2, 3, and 8. And your range would be 0, 24, 48, 72, all the way up to 272 cookies. Looking at 9, says determine whether the situation is discrete or continuous. Again, how we determine if something is discrete or continuous is we look at the range. Can we have fractional amounts in the range? So, in 9, it says your time in a 5K run, every 15 minutes. Well, in this particular case, we can have time in increments, and we can have distances in increments that are fractional. So this would be considered continuous because you can have both fractional amounts of time and fractional amounts of distance. When we look at 10, it says the number of Valentine's cards sold at Target each day of February. Well, this one would be discrete because you cannot sell a fractional part of a Valentine's Day card. You either sell the whole card or you don't sell any of it. So this would be discrete because you cannot have fractional amounts of cards. When we look at a dog's weight over a course of time in a year, this would be considered continuous because you can have fractional amounts of weight and fractional amounts of a year. Looking at 12, 13, and 14, it wants us to find the range of f of x equals x squared plus 1 for the given domain. So what you'll do is you'll take the domain that they give you and you'll substitute it in for x. So in this first one, we'll have negative 1/2 squared plus 1. Then we'll have 0 squared plus 1. And we'll have 5 squared plus 1. And this will get us our range. So negative 1/2 squared is just 1/4. And 1/4 plus 1 is 1 1/4. When we look at 0 plus 1, that just gives us 1. And 5 plus 1 gives us 6. So our range in this particular case, is 1, 1 1/4, and 6. Remember that when we are listing range, we put it in set notation using the brackets, and we list it in order from least to greatest. In 13, it says find the domain for the range -7, -1, 3, and 11. So this time you're given the range, you're being asked to find the domain. So instead of plugging in the values in for x, we're going to plug them in for f of x because the range goes with our y values, and we know that y and f of x are the same thing. So instead of f of x equals 3x, we'll have -7 equals 3x. We'll have -1 equals 3x. We'll have 3 equals 3x. And we'll have 11 equals 3x. And then we'll solve. So in this first case, we get -7 over 3. Then we get -1/3. We get 1. And we get 11 over 3. So our range for this one is -7 over 3, -1 over 3, 1 and 11 over 3. Now, in this particular case, they're already in order from least to greatest. Looking at the second one, looking at the last one, it says for function m of x is graphed to the right, what is the range? So again, we're looking at the graph. So list the range. We go from bottom to top, put our boundaries. This is continuous data because there's no gaps in the data. There are no gaps in the slide. And so when we list it, we're going to write it as an inequality. So our range, m of x, or if it's easier for you just to write y, and write out, we know that it's going to be between two quantities. We know that it is greater than or equal to -2. And we know that it is less than 3. It does not include 3 because there's an open circle on 3. Okay, 15 says give the domain and the range for each relation. State whether the relation is a function and why. So our domain in this case is -5, 5, and 7. These are all the x values that appear. You do not have to list. Remember that we do not repeat any x values. We don't repeat any y values either when we do the range. We only have to list them once. Our range in this case would be -6, 1, 2, and 3. Again, put them in order from least to greatest, and determine, and don't write any values that repeat. Now, is this a function? The answer to this question is no, and the reason why is because the x's repeat. Is this discrete or continuous? This would be discrete because these values were not listed as an inequality. On 16 it says write the domain and range as an inequality for the function pictured below. So our domain starts here and continues on forever. So we know that our domain starts at -5, and it's any value that is greater than or equal to that. So our domain for this graph would be x is greater than or equal to -5. Our range is a little bit different. We see that our graph is oscillating, that it is going between these two values. Oscillate means to just go back and forth. So our range in the graph that we have right now is between -1 and 1. We're including -1 and we're including 1 because our graph actually touches both of those points. This is a function because it would pass the vertical line test. So this passes our vertical line test, which we can also call the VLT. Create a mapping diagram for this relation, and then we want to identify the domain of the range. Okay, well when we create the mapping, remember that we're not repeating any values. So we have -6, we have 5, we have 8, and then we have 5 again. So we're not going to rewrite the 5. Same thing is going to be true for the y's. We have 3's occurring twice. We're only going to write down one of the 3's. The domain for this mapping is -6, 5, and 8. Once you put them in the mapping, you already have the domain. And the same is true for the range. So your range is -2. If we write it in order, it is -2, 3, and 4. Is this a function? Well, when we map it, okay, we have -6 going to 4. We have 5 going to 3, 8 goes to 3, and 5 goes to -2. This is not a function because we see that 5 is going to 2 different outcomes. So it is not a function because 5, we have an x going to 2 outputs. And in a function, that cannot be the case. Based on the graph, okay, it wants us to identify the x and the the x-intercepts, the y-intercept, and the zeros. So your x-intercepts are where it crosses the x-axis. So your x-intercepts in this case would be at -1, 0, and 2, 0. Remember that your y-intercept is where it crosses the y-axis, and that is at 0, -2. Now, your zeros. So we skipped zeros and went to y-intercept. The reason why we did that is because once we know our x-intercepts, we know our zeros. So our zeros in this case are -1 and 2. The only difference between the x-intercepts and the zeros is that when you're writing the zeros, you don't write out the ordered pair. You just write out the value along the x-axis where your graph becomes 0. So those values would be -1 and 2. Looking at 19, we want to identify the y-intercept. Again, that's where it crosses the y-axis, which would be at 0, 1. And the line of asymptote. Remember that the line of asymptote is the line that is at the bottom of your graph that your graph approaches. Remember that the asymptote is a line that your graph does not drop below. And so our line of asymptote in this case would be the x-axis as our line approaches the x-axis. And that would be a y equals equation, and in this case it would be y equals 0. That will give you the equation for the y, or the x-axis. Now, for this one it says, what is the vertex and the axis of symmetry of the graph? Remember that your vertex is the point that is kind of in the center at the bottom. So your vertex for this particular one would be 0.5 and looks like -6. So your vertex would be -0.5 or -0.5 and -6. It's that point that where your graph starts to turn. This would also be considered our minimum. So your minimum and your maximum are the same as your vertex. In this case, it would be your minimum. Your axis of symmetry is the line that goes through the center of your parabola, that goes to the center of your graph. So it would go through your vertex. So our line of symmetry, or our axis of symmetry, is an x equals equation. And to figure out the value that it's equal to, we look at the x-axis and we see that it goes through -0.5. So our axis of symmetry would be x equals -0.5.